Consistency guarantees. In problems with replication lag on page 161, we looked at some timing issues that occur in a replicated database. If you look at two database nodes at the same moment in time, you're likely to see different data on the two nodes because write requests arrive on different nodes at different times. These inconsistencies occur no matter what replication method the database uses: single leader, multi-leader, or leaderless replication. Most replicated databases provide at least eventual consistency, which means that if you stop writing to the database and wait for some unspecified length of time, then eventually all read requests will return the same value. In other words, the inconsistency is temporary, and it eventually resolves itself, assuming that any faults in the network are also eventually repaired. A better name for eventual consistency may be convergence, as we'd expect all replicas to eventually converge to the same value. However, this is a very weak guarantee. It doesn't say anything about when the replicas will converge. Until the time of convergence, reads could return anything or nothing. For example, if you write a value and then immediately read it again, there is no guarantee that you will see the value you just wrote, because the read may be routed to a different replica. See reading your own writes on page 162. Eventual consistency is hard for application developers because it is so different from the behavior of variables in a normal single-threaded program. If you assign a value to a variable and then read it shortly afterward, you don't expect to read back the old value, or for the read to fail. A database looks superficially like a variable that you can read and write, but in fact it has much more complicated semantics. When working with a database that provides only weak guarantees, you need to be constantly aware of its limitations and not accidentally assume too much. Bugs are often subtle and hard to find by testing, because the application may work well most of the time. The edge cases of eventual consistency only become apparent when there is a fault in the system, for example a network interruption or at high concurrency. In this chapter we will explore stronger consistency models that data systems may choose to provide. They don't come for free. Systems with stronger guarantees may have worse performance or be less fault-tolerant than systems with weaker guarantees. Nevertheless, stronger guarantees can be appealing because they are easier to use correctly. Once you have seen a few different consistency models, you'll be in a better position to decide which one best fits your needs. There is some similarity between distributed consistency models and the hierarchy of transaction isolation levels we discussed previously. See weak isolation levels on page 233. But while there is some overlap, they are mostly independent concerns. Transaction isolation is primarily about avoiding race conditions due to concurrently executing transactions, whereas distributed consistency is mostly about coordinating the state of replicas in the face of delays and faults. This chapter covers a broad range of topics, but as we shall see, these areas are in fact deeply linked. We will start by looking at one of the strongest consistency models in common use, linearizability, and examine its pros and cons. We'll then examine the issue of ordering events in a distributed system, ordering guarantees on page 339, particularly around causality and total ordering. In the third section, distributed transactions and consensus on page 352, we will explore how to atomically commit a distributed transaction, which will finally lead us toward solutions for the consensus problem. Linearizability. In an eventually consistent database, if you ask two different replicas the same question at the same time, you may get two different answers. That's confusing. Wouldn't it be a lot simpler if the database could give the illusion that there is only one replica, i.e. only one copy of the data? Then every client would have the same view of the data, and you wouldn't have to worry about replication lag. This is the idea behind linearizability, also known as atomic consistency, strong consistency, immediate consistency, or external consistency. The exact definition of linearizability is quite subtle, and we will explore it in the rest of this section. But the basic idea is to make a system appear as if there were only one copy of the data, and all operations on it are atomic. With this guarantee, even though there may be multiple replicas in reality, the application does not need to worry about them. In a linearizable system, as soon as one client successfully completes a write, all clients reading from the database must be able to see the value just written. Maintaining the illusion of a single copy of the data means guaranteeing that the value read is the most recent, up-to-date value and doesn't come from a stale cache or replica. In other words, linearizability is a recency guarantee. To clarify this idea, let's look at an example of a system that is not linearizable. Figure 9-1. This system is not linearizable, causing football fans to be confused. If Alice and Bob had hit reload at the same time, it would have been less surprising if they had gotten two different query results, because they wouldn't know at exactly what time their respective requests were processed by the server. However, Bob knows that he hit the reload button initiated his query after he heard Alice exclaim the final score, and therefore he expects his query result to be at least as recent as Alice's. The fact that his query returned a stale result is a violation of linearizability. What makes a system linearizable? The basic idea behind linearizability is simple: to make a system appear as if there is only a single copy of the data. However, nailing down precisely what that means actually requires some care. In order to understand linearizability better, let's look at some more examples. Figure 9-2. If a read request is concurrent with a write request, it may return either the old or the new value. For simplicity, Figure 9-2 shows only the requests from the client's point of view, not the internals of the database. Each bar is a request made by a client, where the start of a bar is the time when the request was sent, and the end of a bar is when the response was received by the client. Due to variable network delays, a client doesn't know why. A subtle detail of this diagram is that it assumes the existence of a global clock, represented by the horizontal axis. Even though real systems typically don't have accurate clocks, see unreliable clocks on page 287. This assumption is okay. For the purposes of analyzing a distributed algorithm, we may pretend that an accurate global clock exists, as long as the algorithm doesn't have access to it. Instead, the algorithm can only see a mangled approximation of real time, as produced by a quartz oscillator and an TP-Roman2. A register in which reads may return either the old or the new value if they are concurrent with a write is known as a regular register. Exactly when the database processed its request, it only knows that it must have happened sometime between the client sending the request and receiving the response. In this example, the register has two types of operations. Figure 9-4. Visualizing the points in time at which the reads and writes appear to have taken effect. The final read by B is not linearizable. Read XV means the client requested to read the value of register X, and the database returned the value V. Write X DR means the client requested to set the register X to value V, and the database returned response R, which could be OK or error. In Figure 9-2, the value of X is initially 0, and client C performs a write request to set it to 1. While this is happening, clients A and B are repeatedly polling the database to read the latest value. What are the possible responses that A and B might get for their read requests? The first read operation by client A completes before the write begins, so it must definitely return the old value 0. The last read by client A begins after the write has completed, so it must definitely return the new value 1 if the database is linearizable. We know that the write must have been processed sometime between the start and end of the write operation, and the read must have been processed sometime between the start and end of the read operation. If the read started after the write ended, then the read must have been processed after the write, and therefore it must see the new value that was written. Any read operations that overlap in time with the write operation might return either 0 or 1, because we don't know whether or not the write has taken effect at the time when the read operation is processed. These operations are concurrent with the write. However, that is not yet sufficient to fully describe linearizability. If reads that are concurrent with a write can return either the old or the new value, then readers could see a value flip back and forth between the old and the new value several times while a write is going on. That is not what we expect of a system that emulates a single copy of the data. Roman 2. To make the system linearizable, we need to add another constraint, illustrated in Figure 9-3. Figure 9-3. After any one read has returned the new value, all following reads on the same or other clients must also return the new value. In a linearizable system, we imagine that there must be some point in time between the start and end of the write operation, at which the value of X atomically flips from 0 to 1. Thus, if one client's read returns the new value 1, all subsequent reads must also return the new value, even if the write operation has not yet completed. This timing dependency is illustrated with an arrow in Figure 9-3. Client A is the first to read the new value, 1. Just after A's read returns, B begins a new read. Since B's read occurs strictly after A's read, it must also return 1, even though the write by C is still ongoing. It's the same situation as with Alice and Bob in Figure 9-1. After Alice has read the new value, Bob also expects to read the new value. We can further refine this timing diagram to visualize each operation taking effect atomically at some point in time. A more complex example is shown in Figure 9-4. In Figure 9-4 we add a third type of operation besides read and write. Cas X, Vald, VNUR means the client requested an atomic compare and set operation. See compare and set on page 245. If the current value of the register X equals Vald, it should be atomically set to VNU. If X not equal to Vald, then the operation should leave the register unchanged and return an error. R is the database's response, OK or error. Each operation in Figure 9-4 is marked with a vertical line inside the bar for each operation at the time when we think the operation was executed. Those markers are joined up in a sequential order, and the result must be a valid sequence of reads and writes for a register. Every read must return the values set by the most recent write. The requirement of linearizability is that the lines joining up the operation markers always move forward in time from left to right, never backward. This requirement ensures the recency guarantee we discussed earlier. Once a new value has been written or read, all subsequent reads see the value that was written until it is overwritten again. There are a few interesting details to point out in Figure 9-4. First, client B sent a request to read X, then client D sent a request to set X to 0, and then client A sent a request to set X to 1. Nevertheless, the value returned to B's read is 1, the value written by A. This is okay. It means that the database first processed D's write, then A's write, and finally B's read. Although this is not the order in which the requests were sent, it's an acceptable order, because the three requests are concurrent. Perhaps B's read request was slightly delayed in the network, so it only reached the database after the two writes. Client B's read returned 1 before client A received its response from the database, saying that the write of the value 1 was successful. This is also okay. It doesn't mean the value was read before it was written. It just means the OK response from the database to client A was slightly delayed in the network. This model doesn't assume any transaction isolation. Another client may change a value at any time. For example, C first reads 1 and then reads 2, because the value was changed by B between the two reads. An atomic compare and set cas operation can be used to check the value hasn't been concurrently changed by another client. B and C's cas requests succeed, but D's cas request fails by the time the database processes it. The value of X is no longer 0. The final read by client B in a shaded bar is not linearizable. The operation is concurrent with C's cas write, which updates X from 2 to 4. In the absence of other requests, it would be okay for B's read to return 2. However, client A has already read the new value 4 before B's read started, so B is not allowed to read an older value than A. Again, it's the same situation as with Alice and Bob in Figure 9-1. That is the intuition behind linearizability. The formal definition describes it more precisely. It is possible, though computationally expensive, to test whether a system's behavior is linearizable by recording the timings of all requests and responses, and checking whether they can be arranged into a valid sequential order.